Okay, we'll start. Um, yes, 6, 5. Okay, so good evening all. Myself Akhil. I'm a PhD scholar from IIT Delhi. I'm currently in my fourth year of my PhD and I'm working under the supervision of Professor Dhanya. And my research area is groundwater modeling. I did my BTech in the year 2018 from NIT Calicut in civil engineering discipline, and then I did my MTech from IIT Guwahati in water resources engineering and management under the supervision of Professor Srija Pekar. And currently, I'm enrolled for PhD in IIT Delhi from the year 2022. So, I will begin the section. So, if you have attending my section for the first time, so the pattern which I follow basically is I have divided the questions in such a way that the entire portions which are covered in the previous week, that is the week 5, it will be the theory part will be almost covered. It would be like a recap for you in the through the multiple choice questions. We will be trying to cover the entire portions that have been taken in the previous week. And then we have the numerical answer type, NAT type questions, which would be like an exercise for you to practice similar problems that have been solved in the lecture and also while trying to solve your assignments. So, to begin with, in week 5 lecture, it was basically about another important hydrological process that is infiltration, right? So, the very first class, we introduced you about the hydrological cycle. Then we introduced you about the different processes that are involved in the hydrological cycle. First, we tried to model, and before that, we were introduced with a theorem that will help us to apply the uh, this loss of motions to fluids. That is called the Reynolds transport theorem or RTT. And then we saw how in each of the each of the what we say the hydrological processes can be modeled with the help of this RTT. So the first few lectures we saw how the how atmospheric water can be modeled and all the processes involved in atmospheric water, that is precipitation, evapotranspiration. Then we come to the subsurface, that is the precipitation has occurred and the water has reached the ground and now it has infiltrated and it is reaching the subsurface. And now how the different processes involved in the subsurface can be modeled using RTT, and also which are the important processes which are happening within the Earth's subsurface. These are the main things which are being uh, studied in this particular week lecture, that is week 5. Okay, so we can start with the very first question, that is in unsaturated flow. So we are dealing with the unsaturated portion. So before I start, I will give a brief about what is there in the subsurface. So we already saw what all happened in the above, in the surface. But in the surface, we have not covered this runoff part that we'll be covering in the coming lectures. But we saw how the water, atmospheric water, that has reached the atmosphere and it is through the process of condensation, the clouds are formed. It will come down as precipitation. You already saw how the precipitation is measured, how the precipitation is represented, and also how different analysis we can do with the precipitation. Similarly, now we'll be seeing that once the precipitation has reached the ground, it is going to the subsurface, right? So if this is the ground surface, this particular line is the ground surface. So this is the ground level. Below the ground level, we have two zones. So this particular zone, so this particular line shows the groundwater table. So we have the groundwater, right? Groundwater there within the in the subsurface. So if we see through the well, the water that well maintains is our groundwater level. So we have the groundwater here. So the portion of subsurface above groundwater level, this is called the unsaturated zone. and the portion of water below the subsurface that is called the saturated zone, right? And just above and below at the bottom we have the hard rock strata, or we call it as a bedrock, right? So this is impermeable bedrocks. So this is a very simple representation of the subsurface. And now we need to see what are the important hydrological processes happening in this subsurface. So the very first class, when we are trying to represent the hydrological cycle, there were two things that was clear. One was the water that infiltrates, water that reaches the subsurface will be flowing along the uh, s- surface just below the subsurface and meeting some streams. So this particular flow is called interflow, right? So this was already introduced to you in the very first class. This is called interflow. That is flow in the unsaturated zone that and the water moves to the streams or it meets the nearby rivers. So that particular flow is called the interflow or the flow in the unsaturated zone. Unsaturated zone. And then we have the groundwater flow, right? So that is when there is a gradient difference. When there is a gradient difference in the groundwater, the groundwater levels, the groundwater will flow from the higher gradient to the lower gradient, right? So that is, and this will be reaching a stream. If this reaches a stream or a river, if this groundwater level meets a stream or a river, and that particular process is called, this particular flow process is called base flow, or it is we can call it as flow in saturated zone. So basically, the one thing that you need to understand is that this flow will take place only when there is a gradient. There is a change in groundwater level, or change in there is a drop in groundwater level or something. There should be a gradient difference or the head difference, then only these flows will occur. Okay, so these will be meeting a stream or a river whenever. So if I could expand this and show expand this particular line groundwater level if the elevation drops, and in this way the terrain looks somewhat like this. There was a flat surface and then when it extends it goes down and then like this, and this is the groundwater table if I extend. So here it will be meeting the river. So this particular flow that meters the stream is called the groundwater flow or the groundwater flow or the base flow. And this particular flow along the surface following the terrain path elevation of the terrain, it is called the interflow. These are the one couple of different fluxes that are there in the subsurface. Along with that, different processes are the main processes is how the water that uh, flows down the subsurface, or we can say infiltrates down to the subsurface and finally reaches, then it starts uh, percolating far depth into the and reaches the groundwater level. So this process, that is a process of infiltrating to the just to the subsurface. That particular process is called, which happens at the ground level, that is called infiltration. So we have the main process, that is how the water from the ground level penetrates or infiltrates into the subsurface. That particular process is called infiltration. Once infiltration happens over time, then this water will be percolating deeper and reaching the groundwater level. Okay, so and this infiltration, so in the subsurface, it happens in a subsurface medium, and mainly in subsurface we have two types of particles that are soil and rocks. These are the two materials or particles that are present in the subsurface, that is soil and rock, right? And collectively, we'll be calling, in this particular lecture, we will be calling the subsurface as a porous medium. So porous medium is nothing but a medium which has pores, and the water and the flow will be taking place through these pores, right? And one more basic thing, like an introduction I want to mention. So in the porous medium, if I could represent it like a vertical column, then it has three things. It has the soil particle, so it has a soil particle, and it has void spaces. So basically, the flow will take place through the void spaces. So essentially, this void will be filled by both water and air, right? So when the void spaces are completely filled with water, then we call it as saturated. That will be a groundwater flow. When the flow takes place, when these void space are partially filled by water, that is called an unsaturated flow or interflow. So we will be basically modeling, trying to model the interflow, right? The interflow, we are in this particular syllabus, we will be only modeling the interflow, how the groundwater or the how the flow takes place through a unsaturated medium, not a saturated medium that has the voids will be having both what to say air and water. So that particular thing we will be modeling in this particular lecture. Okay. So the first question, in an unsaturated flow through porous medium, so unsaturated flow is clear for you and porous medium is also clear. The velocity of the flow is generally low. So compared to the surface water flows, the surface water flow, for example, if you take the case of a river flow, the velocity of the flow will be very high, right? So compared to that, to the tiny pores of the subsurface, the flow velocity will be very less. Okay. Because of this, the total energy driving the flow of water is primarily considered to be the sum of two components. So we are asked what is the total energy that is driving this particular flow. So when it comes to the total energy, so if we have through if through basis physics we know or the fluid mechanics, the concept of fluid mechanics we know. Whenever we discuss about total energy, the one thing that comes to our mind is the Bernoulli's theorem, right? So Bernoulli's theorem says the total energy or total head. So energy can be represented in terms of head also. The total energy is equal to a sum of kinetic energy plus potential energy plus the pressure energy. Right. So this is what is given by Bernoulli. Right. So this is from basics fluid mechanics. So we already know that. So now they are asking us the total energy that is driving the unsaturated flow in the unsaturated medium. So what is the total energy? So total energy here in mathematically we can write it as in case of if we apply this to a unsaturated medium, when we apply this to an unsaturated medium, we can say the total energy or the total head is equal to sum of kinetic energy. Uh, so kinetic energy is goes due to the movement, right? Due to the flow. So it is also called the velocity head. Velocity head plus the datum head. So datum is nothing but a representative line within about which we are measuring. So higher the elevation from the representative line, higher will be the datum. So it is proxy to, it is similar to the potential, it's representing the potential energy, right? Datum head plus the pressure head. We will be saying here in the subsurface, we know our subs in the subsurface, our pressure will be less than the atmospheric pressure, right? So that is one more thing that you have to note here in the subsurface. This particular line that we are calling has the groundwater table. This particular line will be at, this will be at atmospheric pressure. So below this P, below GWL groundwater level will be greater than PATM, and P here, P above groundwater table or groundwater level will be less than PATM. So if it is less than PATM, then it will be a suction, right? So there will be a suction. So this suction is mainly sucking the water, or the drawing the water into the subsurface. So there will be having a pressure less than the PATM. That's why we call that pressure as suction, or suction pressure, suction head. These are the three heads basically. So we have the velocity head, the datum head, and suction head. So this is how we represent the head, total head in a porous medium, unsaturated porous medium. And this particular head is driving the groundwater, or driving the flow in the unsaturated porous medium, right? So if you take two locations, 1 and 2, so here we have the total energy H1, and here we have the total energy H2. If H1 is greater than H2, right? So H1 minus H2 is equal to delta H. That is the head difference. So this head difference, or this energy difference, is what that is driving the uh, flow in the unsaturated medium. Okay. So in the question they have mentioned. Also you, it is clear to you that the velocity of flow in the subsurface is very less compared to the velocity of the flow in the surface and all. Right. So here, mathematically, we can write this as total head capital H, or can write it as small h. Small h is equal to v square by 2g is the velocity head. Datum head is z, and suction head we are representing in here is psi. The psi is used to represent suction head. And the velocity is low, right? So we can eliminate this particular term. And so the total head will be a sum of Z plus datum head plus suction head. So this is the head that is driving the flow in a unsaturated medium, right? So here Z is nothing but datum head, and psi is nothing but suction head. So velocity is negligible. That's why we are not considering the velocity head, right? So if you see the options, first option is kinetic energy head and datum head. So kinetic energy head is zero, so that is wrong. Suction head and datum, right? Yes, that is correct, right? So B is the correct option. Third option is kinetic energy head and suction head. No, and pressure head and kinetic energy head. So pressure head is nothing but here the suction head. The correct option is option B. So the main takeaway is the total head, that is, or the head that is driving the flow in a uh, unsaturated porous medium is the suction head and the datum head. Right. So we can move to the next question. So the next question is, the Richards equation, that is the fundamental governing one-dimensional unsteady unsaturated flow, in porous medium. The equation is derived by coupling two fundamental principles. So in this question, they are talking about a equation that is called the Richards equation. So they are also mentioned what is the Richards equation. So it is a fundamental or the governing equation for one-dimensional, unsteady, unsaturated flow in the porous medium. Right. So how they are derived by coupling two fundamental equations, which are the two fundamental principles, or what are the fundamental laws or principal equations that are used to derive the Richards equation. So let's see what the Richards equation is. So basically, from the question itself, they have mentioned it is a one dimensional. So we can see each term one dimensional plus unsteady and unsaturated flow. Unsaturated, and it happens in porous medium. So from this it is clear, the first thing it is clear that it is one dimensional. So it is we are simplifying it into in one direction, that is in the vertical. So infiltration is a process where the water infiltrates vertically, right? So the lateral movement of water in the xy direction in the subsurface we are neglecting. So that is meant by one dimensional. Next is unsteady. Unsteady means it will be changing with time. So the flow will be changing with time. So we are not considering a case where the flow is independent of time. It is dependent on time. With time, the flow changes, right? With time, the head difference changes. The head that we already found in the first question, this changes. This head, the suction head and the pressure head keeps on varying with time. So that is the case where we consider the unsteady case. And unsaturated. Unsaturated, we already know. So we are trying to model the unsaturated zone, not the saturated. The groundwater flow is not being modeled. So this is basically the governing equation for the flow here. That is the for the interflows to the take place, right? So basically interflow will be a lateral flow, but here we have made the simplification. If we didn't make the simplification for one dimensional, then it can model the interflow also because the flow that happens in the xy direction. Here we'll be mainly focusing on the flow in the vertical direction, that is infiltration, we are calling that. So interflow is something that happens in the XY direction, right? In the Z direction, the vertical direction, the process that happens is called the infiltration. So here we'll be modeling the infiltration. That's why we are considering only one dimensional. Okay, if you want to model the interflow or the lateral flow happening in the unsaturated zone, we need to go for a complete 3D representation of Richards equation. So in this syllabus, we are focusing on only the one-dimensional form. That is because we want to try to model the major process, that is the main process is infiltration. So we are not trying to model the other minor process, that is the that is called the interflow, right? So you have to keep that in mind. 1D because we are modeling the vertical flow only in the porous medium, right? So, and this particular vertical flow is called infiltration. So basically, we can say the one-dimensional flow, one-dimensional unsteady and saturated flow basically is trying to model the infiltration process which is a part of the hydrological process, right? Okay. So how this Richards equation? Now let's move on to the Richards equation. So basically, uh, if we have gone to the lecture, basically we derive the uh, Richards equation by combining two equations, that is for one dimensional case, for 1D case, we take two equations, that is 1D unsteady, unsaturated flow, we take two equations. The first one is the continuity equation, and the second one is the momentum equation. But if you see the options, we don't have an option satisfying these both. There is Darcy law and continuity equation. That is one option is there, but there is nothing like continuity and momentum. That combination is not there. So basically, what we does is here by applying the so to apply this first we will see the continuity equation. To apply the continuity equation, we will be considering a control volume. So let this be the control. So control volume here will be a small element, cubical element, cuboidal element along the x, y, and z axis. It is lying in this way. This is the x-axis, this is the y-axis, and z-axis. And this is one dimension. So flow is taking place in the z direction, right? And x and y, the flow is not taking place. So this element has height dz with dy length dx. So this dx, dy, dz is the control volume that we are considering within in the subsurface. And there will be a flux of water that is moving in the vertical direction, right? So that flux we are considering as Q. And this particular flux Q, that is the flow of water through the soil. So this is nothing but flow of water through soil. This flux is can be represented as the discharge, that is total discharge of water happening by the area. And we are calling this discharge as the Darcy flux. So Darcy is the name of the scientist who has did some experiment and come up with the quantification of this particular flux, relating it to the head loss. So this is called Darcy flux. Okay, and so this is the flux we are considering at this particular location, and at this particular location it would be by using the differential statistics dq by d is changing in the z direction, right? dz into dou q by dou z into dz. So this would be the flux in uh, what we say that is coming out. That is, this is the influx or inflow, and this is the outflow, right? And based on this, if you have seen the lecture, we will be deriving our, based considering this particular control volume, we will be deriving our continuity equation. And the continuity equation was coming out to be dou q by dou z plus dou theta by dou t is equal to 0, right? So this is the continuity equation. Continuity equation of 1D unsteady unsteady flow, unsteady unsaturated flow. Right, so here you can see it is changing with time. That's why dou theta. So here theta is nothing but the moisture content, volumetric moisture content in the soil, right? Moisture content. And Q is the Darcy flux. So Darcy flux change in the z direction, and the volumetric moisture content change with time. So that's that is along these two changes are representing the continuity equation in the uh, unsaturated and steady flow, right? And then for the momentum equation case, we are not applying the RTT here for the momentum part. So we are relating this to the Darcy flux. So for momentum equation, we are relating the Darcy Darcy flux Q to the rate of head loss per unit length of medium that we are representing by SF. So they are saying in momentum equation what we are saying for the rate is we are equating it into K into SF. SF is nothing but the rate of head loss that is happening within the uh, rate of head loss that is happening. So head loss is something that head we already saw, right? The head loss, the change in head is driving this process, right? This particular flow is being driven by this change in head. So a constant multiplied by SF, uh, this gives the Darcy's flux. And also, if we take two sections, we can simplify this as Q is equal to minus K into dou H by dou Z, right? Where SF is nothing but change in head it's a rate of change of head in the Z direction. And negative means the flow is taking place opposite. So the y-axis, z-axis above is in the positive will be if the flux is moving above, right? It is going down. So that's why we have the negative sign. Or we can say because the head is changing, the head will be dropping. So it's a drop in head, right? So if we combine both, so this is how the momentum equation here we are instead of applying an RTT for the momentum equation, we are relating it to the Darcy flux. So this is something, this particular relation is something that we got by applying the RTT theorem to a flow through a laminar flow through a pipe flow. So that is that same equation that we have already derived. So if you have seen the lecture, we would be getting something related to this, right? So that equation we already got. So that is also a fluid part, right? The water that is flowing through a pipe or the closed conduit. So that uh, that also related the flux or the discharge of the pipe to the uh, Lawson head, right? So that same concept we are using here, and we are relating the Darcy flux with the this particular concept of flow of through pipe, laminar flow through pipes in a porous medium. And that's why we are getting this. Essentially, we have already applied the RTT while deriving the laminar flow through a closed conduit. So that's why we have, in a way, we have already applied the RTT and got this equation. Now we are just relating it, right? And finally, when we combine this, we'll be getting a relation d theta by dt that is combining both momentum and the continuity equation. Dou by dou is d into dou theta by dou z plus k. So this particular equation is called the Richards equation, and it represents 1D, the unsteady plus unsaturated flow through porous medium. Right. So I hope it is clear. So only thing you have to remember how we end up with this equation. So here, one more thing I wanted to highlight is what is this K? This particular K is nothing but the hydraulic conductivity. So K is nothing but the hydraulic It's a constant conductivity of the porous medium. How you get this particular value is we for different soil textures. Like if you take a soil texture like a loamy soil or a clay soil or a sandy soil, for each of the soil textures we will be having a particular range of value for K. That is how we will be getting the hydraulic conductivity, right? And so if we have this, we can model the 1D unsteady unsaturated flow through a porous medium. So this is the famous Richards equation, and the only thing that you have to remember how we are getting this, we are getting this by making use of continuity and momentum equation. But here, continuity equation we derived using the control volume concept and we applied RTT. But in case of momentum equation, we are relating this to the this Darcy flux that flows through the control volume to a flow through a closed conduit where lamina flow through a closed conduit, and that particular momentum equation for a closed lamina flow through a closed conduit we have already derived using the RTT. If you have seen lectures, you will be remembering that. Okay, so we are relating that and then we are coming up to this. So we can say that the flow through a closed conduit or laminar flow that is happening, that we are relating to the Darcy flux and we are coming up this particular expression. So that is the background of the Richards equation that should be. And now if we come to the options, the first option is Darcy's law and continuity equation. So this is the option one is a most suitable answer, right? Because it has we are applying Darcy's law. Darcy's law is nothing but this particular we are able to come up with. So this is called Darcy's law. This particular expression over here minus q is equal to minus q is equal to minus k. So this is called Darcy's law. So we're ending up to the Darcy's law. How? Because we were able to relate this to the flow through laminar form, the momentum equation of a flow through in a closed conduit, the laminar flow in a closed conduit. Okay, so this is the correct answer. So all the Hagen-Boerstler equation and energy equation, no Newton's second law and momentum equation, both are the same. Renamed and approximation and Darcy's law. This is also wrong. Okay, so that is a brief introduction of the charts equation, how we are coming up, how we are using the concept of RTT and coming up and deriving this particular. So the next question is, during a storm event, if the rainfall intensity is I, so the intensity of the rainfall is I, it is happening at I rate. Intensity unit you already know, right? Mm per hour or length per time is less than or equal to the the potential filtration capacity of the soil FP. So we need to know what is potential infiltration capacity of a soil and what will be the actual infiltration capacity. So in case of a, so here we need to know about two terms, that is FP and FA, and how it is connected with rainfall intensity. So this is something that is important here. Okay, so, so from the terminology itself, it is clear. So this, from the first part of the question, rainfall is happening, and the rainfall intensity is I. So rainfall is occurring at I rate, right? So if rainfall is occurring at that rate, which is higher than that of the soil can absorb, then infiltration will be at the maximum rate, right? So if rainfall is occurring at a rate that is higher than what a soil can absorb, right? There is a maximum limit to the infiltration that can happen at a particular time. So if the rainfall intensity is greater than the rate of the rainfall that is happening is greater than that particular threshold, then the intensity won't be, the infiltration won't be increasing. It will be reaching the maximum capacity, right? So that particular thing, we are calling it as uh, potential infiltration capacity. So the FP, that is FP or potential infiltration capacity, that is maximum how much water can be infiltrated at what rate, maximum how much how what is the maximum rate at which the water can be infiltrated, right? So that is uh, given by, or that is defined by FP, right? So if the rainfall, and we can see what is FA also. So sometimes, all the time, the rate of the infiltration won't be the maximum. That much rainfall won't be available, right? If rainfall is this, that much it won't be infiltrated. That much water is not available, then it will be won't be infiltrating at that particular rate. This is similar to the potential and actual evapotranspiration that we already saw in the previous lecture, right? So here, FA is an actual infiltration rate. So that is if plenty of water is available through rainfall. If rainfall is happening in a very high intensity or that particular intensity that is able to satisfy the maximum infiltration capacity, and then the infiltration will be taking place at the rate of FP. And if the infiltration capacity is lower, then lower than the FP, then if the rainfall intensity is less compared to FP, then the rate at which the infiltration happening is called the actual infiltration. Right. So let's take two cases. That is one if, so case one, when I is greater than FP. So rainfall is happening at a particular rate I that is greater than FP, then we can call this, then the actual evapotranspiration, that is or the actual infiltration will be equal to FP. So it can have a maximum infiltration of FP only, right? Even if the intensity I is greater than FP, that much cannot be infiltrated. Only maximum FP can be infiltrated. The second case is I is less than FP. That is, rainfall that is happening is less than the maximum infiltration rate. Then the actual infiltration happening will be equal to I, right? The rate of the infiltration. That will be same as the rate of infiltration. That is the second case. Okay. So these are the two important things. Uh, that is how the for different intensity of rainfall, how the infiltration is happening. So this is similar to the concept of actual evapotranspiration and the potential evapotranspiration. So now let's come to the question. Here, rainfall intensity, they are mentioning it as less than or equal to the potential evapotranspiration. So here in the question, I is less than FP, right? So FA we already know will be equal to I. And they are asking us what is SA. It will be equal to potential. So first one is wrong. Equal to the rainfall intensity. Yes. All the rest of it is equal to 0. That is wrong. It is the average of I and B. That is also wrong. Okay. So only thing that you have to keep in mind is infiltration has a maximum limit. It won't increase by with rainfall increasing. Maximum will be equal to less than or equal to the one particular capacity that is called the potential evaporation rate. So coming to the next question that is related to how we measure infiltration experimentally. So two things we can do, we can measure infiltration or we can estimate infiltration. Estimation is done using these analytical methods or these equations, mathematical equations. Measurement is called the field measurements, that is experimental techniques. So why is double infiltrometer preferred over single infiltrometer while measuring the infiltration rate? So you need to know what is the infiltrometer and what is double and single infiltrometer. Okay, so we'll directly come to the double ring infiltrometer. So there are two types of techniques to measure the infiltration. Can be measured using head-based techniques. Different head-based techniques can be used to measure infiltration. These are called single ring infiltrometer and double ring infiltrometer. So in a single ring infiltrometer, if you could see the cross section, so the front view. So this is the front view of the ring. Okay, and what we'll do, we will insert this into the ground at some centimeters into the ground. We will hammer it into the ground, and it is the around 15 centimeter. We'll insert it into the ground, and we will fill this with water. And this will be filled with water. So here what happens is the water starts infiltrating, right? So it will infiltrate, right? But in the edges, if you see, water can infiltrate to the sides. So so then what we do is we will be keep on measuring the water that is there in this particular ring with time. So we'll make a column of time and head. And through this head differences, we can measure the infiltration rate. So that is the functioning of an infiltrometer. So in case of a single ring infiltrometer, the problem is whatever we are finding won't be accurately equal to infiltration because the sum of the lateral flow is also taking place. So infiltration is a process where the water percolates in the z direction only, right? And the Richards equation, through that if we solve equation, we are taking the one-dimensional Richards equation because we are approximating it to the along the z direction along. But here, what we'll be getting will be a combination of z and xy. Flow will be can also takes place, right? So it won't be that accurate. So that's why they have introduced a double ring infiltrometer. So it is similar to this. The only difference is instead of a single ring here, it will be having two rings. So this is the inner ring and outer to this. And outer to this we'll be having another ring. Right. And what we'll be basically doing, we'll be filling water both in the inner ring. So the inner ring will be filled up with water, and also the outer ring will be also filled by water. So this the gap between the inner and outer. There also we'll be filling it with water. So this is the ground level. Here, this also we'll be hammering it into the ground, and we'll be filling the inner ring and outer ring. Both we'll be hammering into the ground. Will be hammered into the ground. The advantage of doing this is that anyway we'll be measuring the infiltration or the head change in the inner ring alone. We won't be measuring the outer ring. The water is filled in the outer ring only to avoid the lateral flows, right? So when happens, the infiltration will be happening in this layer, right? Only the issue of the lateral flow or the flow in the XY direction was coming towards the edges, right? So here also that issue will be there, that will be in the outer ring. It won't be disturbing the inner ring, right? So here the inner ring will be getting a perfect 1D, one-dimensional infiltration, one-directional flow. So we'll be getting more accurate infiltration rates. That is the advantage of using a double ring infiltrometer over a single ring infiltrometer. Okay, so these are the two of the most common experimental field measurement techniques used. We can also measure, if we have the soil sample, we can also measure the infiltration in the labs. That is using instruments called mini disc infiltrometer that is already discussed in the lecture. So if you see the options, it requires less water to conduct the test. Wrong. The inner ring prevents evaporation to the outer ring. No. The outer ring helps to prevent the lateral spread of water from the inner ring, ensuring one-dimensional vertical flow. Yes. So what I just explained. It allows the measurement of infiltration in two different depths. I must know. So the answer is the outer ring helps to prevent the lateral spread of water, lateral flow of water from the inner ring. Why? Because we are ensuring a one-dimensional flow here. Okay. So we can move to the fifth question. So similar to the evaporation chapter, here also we are measuring infiltration using three methods. One is the experimental methods, and then we are estimating infiltration using empirical, that is using mathematical equations, that is we have the empirical equations and also the analytical equation or theoretical equations. So, so here it is the empirical. First question is related to the empirical equation. So empirical is the scientist, different like a scientist like Horton. They conduct this test on different types of soil samples or different locations, and they come up with a equation to quantify the what we say the infiltration process. They are not solving the Richards equation that we just saw. They are coming up with experimentally. They are coming up with the equations that can give us an estimate of the infiltration that can happen. So one empirical equation is the Horton's equation that is very widely used. Horton's empirical equation model gives f of t, that is infiltration rate at a time t, has fc, that is plus f naught minus fc into e raised to minus kt. So there are different parameters fc. So these are the parameters that we have to look into: fc, f naught, and e raised to k. So there are three parameters. What is fc, f naught, and k? So what does the parameter fc represent? So they are asking us what is fc. So we can like a look at all the three parameters here, right? So the Horton's infiltration technique or the formula or model, Horton's infiltration model. So this is particularly based on, that is, the relationship observed under ponding conditions. So he assumed, Horton, the scientist, he assumed that the infiltration rate, uh, it follows a exponential relationship. That is, a rate at which infiltration occurs will follow an exponential relationship with time. Right? We know that this particular, we know that FC, the infiltration at a time t, Ft, is a function of, it is a function of time, right? So they are assuming that Ft is varies exponentially. So that is the main assumption, or that made by the Horton, right? And he came up with this particular equation: f of t is equal to Fc plus f naught minus Fc e raised to minus kt. So what it basically say is that initially at t equal to 0, f t, if you see, it will be coming around. So this will be 1. Fc gets cancelled, f naught. So it is what is saying at time t equal to 0, infiltration will be happening at a rate of f f naught, right? After that, when t increases, ft reduces or decreases to a constant rate fc exponentially. So this is basically the concept he has used here. So initially at time t equal to 0, right, at time t equal to 0, the infiltration will be happening at a rate f naught, that is initial infiltration rate. Then it decreases exponentially until it reaches a constant rate. So that is if t is infinity. If you take a time t as infinity, then the second term will be almost equal to 0, right? Then ft will be getting it as fc. So after a very long time, we will be getting a constant rate that is called fc. So basically, initially it is f naught and it is exponentially decreasing to a constant rate fc. So if we can show it with the help of a graph, if I plot time in the x-axis and infiltration rate f of t in y-axis, initially it will be f naught, right? And finally it will be reaching a constant rate. So if this is the constant, that is fc, and the curve will be something like this, right? Exponential. This is an exponential curve, exponential decrease. So this is how Horton modeled it. So this particular f naught is nothing but initial infiltration rate, and this particular fc is called steady state constant infiltration rate. So this is nothing but it's called steady state because it is not changing with time and it is remaining constant, right? So from the options, if you see, uh, first one is infiltration capacity T equal to 0. It is not Fc, right? It is Fa. This is strong. So this is basically Fa. The decay constant. So decay constant is nothing but K. So E raised to minus KT exponential TK constant is given by K, right? The final steady state infiltration capacity of the soil. Yes. So the answer is C. And the cumulative infiltration of that is also wrong. So that is about Horton's equation. Let's move on to the next question. So next we'll be looking into an analytical method uh, to measure estimate infiltration. So analytical method are derived by solving the Richards equation. We know the governing equation for the flow in the one-dimensional flow in the unsaturated medium is given by Richards equation. We already saw the equation how we are deriving it. And by solving this Richards equation, so it is, you already know it is a differential equation. By solving that particular differential equation, we can get the infiltration rates, right? So one such attempt was made by Phillips, and he basically what Philip does is he tried to solve the infiltration equation, and he used the solution the method he used to solve it is the infinite series method. So the differential equation, the solution can be given is can be derived by using the infinite series method, right? And he then truncated the series to the first two terms, and then he got this particular equation. So that equation is for the cumulative. So here the cumulative infiltration is given by, it is not f of t, it is capital F of t. So he solved the solution and he got the cumulative infiltration depth as f of t is equal to s t raised to half plus kt. What does s represent? So we need to see what is the parameter s represent this particular equation. Which forces does it primarily account for? Which are the which force that particular s, this particular term, the second term accounts for? So basically, let's look into the Phillips equation. So we know the Richards equation is given by Richards equation is given by dot d theta dot theta by theta is nothing but the volumetric moisture content. Dou by dou instead of d is nothing but the diffusivity of the soil and water plus k. Right. So this is the equation which are a Richards equation for one-dimensional, unsteady, unsaturated flow in porous medium. So analytical solution or theoretical solution will be basically by solving this equation. So what Philip did is, so he used the concept of infinite series to solve this particular differential equation, and then he truncated the series to first two terms. He saw that the first two terms is enough to accurately represent the infiltration. That is what he found. Right. And finally, he came up with this particular equation, f of t. So this is cumulative infiltration depth. So it is in the unit of meter or length unit. So it is not the rate. The cumulative infiltration depth. So after each time, how much more and more water can be infiltrated is given by s t raised to half plus k into t. So we can look into the terms. So f is the cumulative infiltration depth. Cumulative infiltration depth. S is sorptivity K is nothing but in hydraulic conductivity. So the first, the S term S represent the sorptivity of the soil. So sorptivity S, that is sorptivity, is represented as a function of soil suction. That is how much the soil, that particular soil type can suck. The suction for pressure that can be applied by that particular soil type that incorporates. So basically, if it is a function of soil suction, then this particular term, that is term 1, that is st raised to half, will represent what type of force. We know there are two, the total head was given by the suction pressure or suction head and the datum head, right? So this represents the suction force. The second term, kt, represent nothing but the gravity force. K is nothing but the hydraulic conductivity, right? So if K is a hydraulic conductivity, and that is something related to the uh, flow that is happening in the soil, right? In the unsaturated medium. So it represents the gravity head. So, so what happens is, for a better understanding, we can see this equation. That is the first term represent the suction head. That is initially when the infiltration happens, then the head difference won't be much. Then the major force acting will be the suction forces. And when more and more water gets infiltrated, then there will be head differences and they starts flowing. So then the gravity and the flow will be taking place with the gradient differences or the datum differences. So or the gradient differences or the head differences. Then the suction forces, then the gravity forces comes into picture. So initially the dominant will be the suction force, and then the gravity force will be taken into picture. And at any time, the infiltration depth is governed by the sum of the suction force term and the gravity force term. So if you see the options, the option one is stands for saturated index, that is wrong. Sorptivity, yes, it is right, and account for the foil suction forces. Yes, that is the correct answer. Storage coefficient, it is wrong. Specific yield is also wrong. So basically, uh, if you see the analytical theoretical solution given by Philip, it has two terms. First is the suction force term, and second is the gravity force term. And during a rainfall process, when the infiltration starts, then the suction forces will be dominant. The first term will be dominant. Then later on, when the time proceeds, then the flow, mainly the infiltration will be happening due to the head difference, and then the dominant one will be the dynamite or the gravity force. Okay, so that's all about the Phillips equation. So we had one more analytical method, that is Green-Amt equation, so that we'll be seeing through a problem in the numerical type. So we can start with the numerical type questions. So very first question is, the infiltration capacity of a catchment follows Horton's equation, so it is related to the empirical way to estimate infiltration, that is using Horton's equation. So we already saw what is Horton's equation, what are the different terms. So it assumes that the infiltration happens through an initial rate F naught, and then it will be exponentially decreasing and reaching a constant rate Fc. The infiltration capacity is 50 mm. So we can write it down. Infiltration capacity, that is Fc is equal to 50 mm per hour. And the initial infiltration, no, the initial infiltration capacity, so it is F naught, right, not FC. Initial infiltration capacity is either, and the final infiltration capacity FC is 10 mm per hour. That is a constant infiltration rate, or the steady state infiltration that is happening is 10 mm per hour. The decay constant K is 2 per hour, and calculate the cumulative infiltration depth after. So we have to find F after 2 hours of continuous bonding. So this was the assumption. So that is one point which I missed. The assumption of Horton's equation is that there is continuous ponding that is happening. There is no situation that the water, the surface above the surface is not ponded. Every time there is plenty of water that is ponded water is there. So that is an assumption. Okay. So we need to find not the rate, but the actual infiltration happening at after infiltration depth, total infiltration depth after 2 hours. Okay. So we can start with the formula. So the equation is infiltration at any time t, or the infiltration rate at any time t, is given by Fc, that is the max steady state infiltration, F naught minus Fc. F naught is the initial infiltration rate into e raised to minus kT. K is the decay constant. So Fc is 10, F naught is 50 minus 10 into e raised to minus k is 2. K is 2 into t. So this can be simplified as 10 plus 40 e raised to minus 2t. This is f of t. Okay, so we got the equation, Horton's equation for infiltration rate. So if we want the cumulative infiltration rate at any time, capital F of t is nothing but we need to integrate. Integral 0 to till what time we want f of t dt. Right. So here it will be 0 to 2. We need infiltration after 2 hours, right? F of t equations 10 into 40, 10 plus 40 e raised to minus 2t dt. Right. If we integrate this, uh, 10 if we integrate 10t plus 40 e raised to minus 2t divided by minus 2 within the limit 0 to 2. And if we apply the limit 10 into 2 minus 40 e raised to minus 2 into 2, 10 into 0 minus 40 by 2 is a 40 by 2 e raised to 0. So this will be 20 minus 20 e power minus 4. This will be 0 minus 20, right? And finally, we'll be getting the value around 39.6337 mm. This is the total depth of water infiltrated after 2 hours using the Horton's equation. If there is continuous ponding, that is the assumption that we made. And we have been asked to report our answer in 2 decimal places. So we can approximate it as F after 2 hours is equal to 39.63 mm. Okay, so that is the first question related to the Horton's equation. and it's basically an empirical equation that is based on the assumption that continuous bonding is happening, and when the rainfall happens, infiltration will be happening at a rate of F naught, and after some time it will be reduced to a constant rate Fc, and the reduction will follow a exponential path. Okay. Uh, Coming to the next question, that is related to the Phillips equation, so that we just saw. Mm, the cumulative infiltration rate modeled with help using Phillips equation is given by. So this is giving the cumulative infiltration rate. So we have already integrated. If we integrate the previous previously we were seeing the rate equation, right? So if we integrate that, we will be getting this particular equation. It is already given to us. F of t is equal to 4t raised to half plus zero point 0.5. So this is the zero point 0.5 t. So this is the equation for infiltration depth. Phillips equation for cumulative infiltration depth. Okay, so once you have this, they're asking where Ft is the cumulative infiltration depth at T is in centimeter. So Ft in centimeter and T is in hour. So we can note that down. T is given in hours. Calculate the actual infiltration rate. So this is clear. Calculate actual rate at t equal to 4 hours. So basically, this is the opposite of that. We are given with the equation of the cumulative. We need to find the cumulative depth. We have to find the infiltration rate, right? So that will be the opposite of integration. That is differentiation. That is f of t is given. Then we can find small f of t as tf by dt. We can just differentiate that particular equation. That is nothing but df d by dt of 4t raised to half plus 0.5 t. So that will be 4t raised to half, differentiation will be 4 into half t raised to half minus 1, that is minus half, right? Plus 0.115, yes. This will be 2, so it will be coming around 2t raised to minus half plus 0.5. That is nothing but f of at any time t. And the question they have already mentioned, t is in hours, right? So t is in hours, and we will be getting ft in centimeter, right? So we can substitute for 2 hours. No, they have been asking for 4 hours. Okay, so we can substitute this for 4 hours. So it will be 2 into 4 raised to minus half plus 0.5, right? So if you solve this, you will be getting this is 1 plus 0.5, that will be 1.5, and unit of FC is in centimeter. Capital FT was in centimeter, so small ft will be getting in centimeter per hour because time was in hour, right? So the final answer they have asked to report in two decimal places. Final answer is 1 point. So F at 4 hours is equal to 1.50 centimeter per hour. Right, so this is the opposite. So this two relation is clear. If we have the infiltration rate equation, we can integrate it to find the cumulative infiltration depth. And if we are given with the equation of the cumulative infiltration depth, we can differentiate that and get the infiltration rate equation. Okay, so let's move on to the next question. So the question is, an infiltrometer test was conducted to estimate the parameters of Kostyakov infiltration model. So we have not discussed this particular empirical equation. So in addition to the Horton's equation, we were also introduced to Kostyakov infiltration model. So also an empirical equation. It's not an analytical or theoretical equation, it is an empirical equation, right? The measured cumulative infiltration data. So basically, we are dealing with the empirical equation that is called the empirical model, that is Kostyakov infiltration model. So the cumulative infiltration data was measured, that is in centimeter, and time is measured in hours. Okay, so these data they were collected, were performed, were transformed, and plotted as so. And they plotted what they did is they measured the infiltration depth and the width time, and they converted that to ln, natural logarithm of ft, and they plotted that in the y-axis, and ln of t, ln of time, in the x-axis. So they basically made a plot of, in x-axis they plotted ln of t, natural logarithm of t, and y-axis they plotted natural logarithm of ft. And also the point to note, ft they are mentioned in centimeter and t in hours. So say they got different points based on our values, and it is a cumulative plot, right? Ft is cumulative. If you take the logarithm also, the if, when t increases, the ft will be increasing. We will be getting an increasing plot, and they fitted a best line fit they made over this, and they got the best fit. And this particular line equation that will be in the format of y equal to mx plus c, right? So here y is nothing but ln ft is equal to m into ln t plus c. So c is nothing but this particular intercept. So this is c, and this, the slope of this is nothing but m. This theta is equal to m. Slope is equal to m. So the tan theta is equal to m. Right. So this is what they did experimentally. They measured the ft and the t values, and they plotted the natural logarithm of both, and they fitted a linear regression plot, and they got the slope, and they got the slope as the slope of this line, that is m, is equal to 0.6y, and the intercept c is equal to 1.10, right? So the thing what we need to do is basically we need to convert our equation in this format, right? So they are use so Kostyakov equation. So it is given the question. The cumulative infiltration depth is given to this particular equation. K by 1 minus alpha into t raised to 1 minus alpha. So they are asking us to find the empirical parameter kk using this. Okay. So we can write down the equation. So the equation is kk by 1 minus alpha t raised to 1 minus alpha. This is this is nothing but f of capital F of t, right? So we can do one thing. We can take the log in both sides, right? If we take the logarithm in both sides, that is ln f of t is equal to, the first term will be log a into log b will be log a plus log b, right? Log ab is equal to log a plus log b. So log kk by 1 minus alpha plus log b, log of natural log of t raised to 1 minus alpha. This can be written as ln kk 1 minus alpha plus 1 minus alpha. We take an natural logarithm inside, right, of ln t. This is ln of ft. Now you can compare this to the equation of line, that is y is equal to c plus mx. So if our y is nothing but ln of ft and x is nothing but ln of t, then here our m slope will be nothing but 1 minus alpha, and our intercept is nothing but ln of kk by 1 minus alpha. So this two we have all they have already given. So they have fitted the this particular thing and then fitted the plot, and they are given the slope and this value, right? So 1 minus alpha is equal to 0.65 and c is equal to 1.10, right? So 1 minus alpha if is equal to 0.65, then we can find alpha from here. One of the parameters alpha, that alpha will be equal to 0.35, right? And if you substitute that in the second equation, that is ln intercept kk by 1 minus alpha, it is equal to 35 is equal to 1.10. So if you take the exponential, kk by 1 minus 0.35 will be equal to e raised to 1.10, right? Then kk will be equal to 0.65 into e raised to 1.10. And if you calculate this, you'll be getting something around kk is equal to approximately 1.9527. The parameter of the what is it, Kostyakov infiltration method, KKK, is coming out to be 1.9527, and we have asked to report the answer in two decimal places. So the final answer KK will be equal to 1.95. So that is how we solve it. So basically, the what we to fit the to find the parameter, so this parameter will be different for different type of soil, right? So what we do, we perform this experiment using the instruments or something, and we get the infiltration depth and the infiltration cumulative infiltration depth and time, and then we try to take the logarithm of these equations and try to make it in a linear form, and we'll plot those, convert the measured values into the logarithmic form, and then we plot the graph and we fit it with the straight line equation or linear equation. And then we will measure the slope and intercept from the plot, and then we'll relate this to the our equation, and then we'll be getting these parameters. So this is a general technique that can be used to find the parameters of any empirical equation that is uh, that is used to measure infiltration, right? And also, only thing we have to make sure, make only thing that we have to keep in mind is we have to convert the equation by taking logarithm in such a way that it forms a linear fit, or the linear equation, it relates to a equation of a linear or equation of a line in the format of y equal to mx plus a, so that we can plot the best fit line and get the slope, and with the slopes and intercept value we can get the parameters. Okay, so similar questions where like three, four questions, two, three questions were solved in the class. Right. So there we were asked to, you were given with the data and you were asked to plot the data. So in such cases, what we need to do, we should be either plotting in a graph paper and finding the slopes, or we should be plotting it in any of the softwares, like Excel or any of the programming codes you can use to get the plot, do the linear regression and get the slope and the intercept. Right. So we can move on to the next question. It's 10th question. So a soil particle has a total porosity of 0.45. So 0.45 is the porosity, total porosity of the soil particle, and the residual moisture content of theta r. Okay, so the total porosity is 0.45. Porosity is nothing but the uh, it's a ratio of total volume of voids by the total volume, right? Volume of voids by the total volume is gives the porosity, right? And the residual moisture content is given by theta r. So residual moisture content is nothing but if you take a soil sample and you try to dry the soil in a standard temperature and pressure conditions to a standard, that is a standard pressure and temperature, we are drying the soil. So still at that particular temperature, some amount of moisture will be still there in the soil. That particular uh, temperature or that particular moisture content that is still there in the soil, retained in the soil, is called the residual moisture content. Okay, so I hope that is clear. So just before the rainfall even begins, the initial moisture content is theta I. So another uh, compound value, that is theta I, is also given. That is just before the rainfall occurs, what is the moisture content? Theta I, and it is recorded to be 0.15. So initial moisture content is given. Okay, calculate the effective saturation. What is effective saturation? That is another thing that another concept. These all terminologies we have been introduced while we were discussing about the uh, green amp method. Green amp method that is used to, it's another analytical method or theoretical method that is used to solve for the Richards equation, right? So we need to calculate the effective saturation of the soil before the rainfall begins. So we are given with the porosity eta, that is equal to 0.45. This is just to introduce to you with some relations that have been derived, which we'll be using in case of the green amp method. Okay. So eta is given, that porosity is given, theta r is also given, the residual moisture content, that is a moisture content that is there in the uh, soil when it is dried to a standard temperature and pressure. And just before the initial moisture content is recorded to be 0.15, and they have been asked us to find the effective saturation, SE. So the relation is SA is given by theta I minus theta R divided by eta minus theta R. So this is a relation, that is theta I minus theta R by divided by eta minus theta R, right? So here theta I is nothing but initial moisture content, that is 0.15. Residual moisture content is 0.05. So the numerator is nothing but how much actual moisture was there initially. Actual moisture in addition to the residual moisture that was there. 0.15 is the actual moisture content, right? Was there. Out of that, 0.05 something residual moisture content is always there in the soil moisture, in the soil. So how much excess to the residual was there divided by porosity, that is eta Porosity is nothing but 0.45 minus 0.05. So denominator is nothing but how much maximum moisture can be added. It had already a 0.05 moisture content was there. So maximum moisture it can hold is equal to the porosity, right? So how much more moisture in addition to the residual moisture that can be added to make it to the porosity. So that was coming out to be 0.45 minus 0.005. So this will become 0.01 by 0.4. That will be around 0.25. So the effective saturation is given by the excess of moisture that is actually there, the excess to the residual moisture and actually there currently, and maximum more moisture that can be added in addition to the residual moisture is already there to to make the moisture maximum. So the maximum moisture content the soil can hold or soil can retain is nothing but that is equal to the porosity, right? So that two difference ratio gives us the effective saturation. So this we can write it as. So if you don't want to by heart the equation, you just remember effective saturation is nothing but the ratio of how much moisture is currently present in excess to the residual moisture. That is, initially we know the soil will have a residual moisture content. So how much excess to that is there divided by how much excess moisture can be can be added to reach maximum capacity. So maximum capacity is nothing but eta, porosity. So how much excess can be added? So initially already there will be residual moisture content. How much more can be added? Okay. So remember in this way. So we can move on to the next question. So the next question is a small tube with the cross-sectional area of there's a small tube with a cross-sectional area of 40 centimeter square filled with soil and laid horizontally. So here it is an experiment in which a small tube is there. The tube is filled with what we say, filled with soil and laid horizontally. And so it's basically a part of an experiment where we have filled the tube with the closed tube with the of an area of 40 centimeters square with soil and it is laid horizontally. And the open end of the tube is saturated and so the open end of tube is saturated and after 15 minutes 100 centimeter cube of water 100 centimeter 100 centimeter cube of water has been infiltrated into the tube. Okay, so the open end of the tube is saturated and after 15 minutes we can see that 100 centimeter cube of water has been infiltrated. The cube has been infiltrated. The saturated hydraulic conductivity of the soil is 0.4 centimeter per hour. So the hydraulic conductivity K. So we can note down area is given. It is 40 centimeter square and the time T after 15 minutes. The volume infiltrated, total volume. So infiltrated volume is equal to 100 centimeter cube, right? The hydraulic conductivity is given. Capital K is 0.4 centimeter per hour. And if the same soil column has been initially been placed upright vertically, its upper surface saturated, determine the total depth of infiltration it would have taken after t equal to 30 minutes. So initially, the column was kept horizontal. Okay, the column was kept horizontal, and the experiment was conducted, and we have found all this. The area we know that after 15 minutes, 100 centimeter cube of water has been infiltrated. So if we divide that 100 meter cube from the area, we'll be getting the infiltration depth, right? And the conductivity of the soil is also given. And now the same column we are keeping it is in upright the vertical in the vertical direction, and then we are again performing the same experiment, and they are asking how much infiltration depth the cumulative infiltration is happening after 30 minutes. So basically, if we had seen the lectures, the Phillips equation, one of the advantages was that we can apply it into the horizontal columns also. The other equations we were applying to the vertical columns. The Phillips equation, the advantage was we can apply apply that for horizontal columns also. So the Phillips equation we already saw in the previous questions. So the same equation, if I could write down here, so Phillips equation is given by f of t is equal to s t raised to half. S is nothing but the sorptivity and K into T. So we already saw this equation. All what are the terminologies? Everything we saw. K is the hydraulic conductivity. S is the sorptivity, which is a function of soil suction and all. Right. So when this particular equation is applied for a horizontal column, there will be only the suction term. The suction pressure will be there. The gravity term will be vanishing. Right. So what basically this equations? This is the equation for a vertical case. Equation for vertical soil column. For horizontal soil column, the second term, that is the gravity term or the gravity pressure term, will be vanishing, right? So we'll be having this particular equation f of t, cumulative depth after any time t, will be given by s t raised to half. So this is the equation, right? And here in the question they have mentioned the infiltration volume as 100 centimeter cube after 15 minutes, right? And the area is 40 centimeters square. So F after 15 minutes will be equal to volume by area, right? So volume is nothing but 100 centimeter cube divided by area is 40 centimeter square. So that will be around 2.5 centimeter. So the cumulative infiltration depth of water is equal to 2.5 centimeter. So 2.5 centimeter depth of water has infiltrated, right? So we can relate now put in this equation f of t is equal to s t raised to half, and also here um, uh, we have given the hydraulic conductivity, everything is in hours, right? So you have to convert time into hours, right? So for Phillips equation, time is in hours, and we will be getting ft in centimeter per hour, right? So f at time 15 minutes is 15 by 60 hours. That is 0.25, right? Is equal to S. So this is equal to 2.5 centimeter. And so this will be capital FT, and that we'll be getting in centimeter, right? So S of 15 is 0.25, T is equal to 0.25 raised to half, that is equal to 2.5. So S will be nothing but 2.5 divided by 0.25, the whole raised to half. That will be coming around 5 centimeter per hour raised to half. So through this, we are able to find one of the parameter, that is sorptivity of the soil, that is equal to 5 centimeter per hour. Now, the next part of the question is we are inverting the soil column. So we are keeping it in vertical direction. Earlier it was in horizontal direction. Then the equation that we need to use, it will be having both the term, the suction term and the gravity term. So the cumulative depth will be given by the suction term, that is St raised to half, and the gravity term, that is given by Kt. Right, these two, it will be a part given by these two equations. So St raised to half, so we can substitute values here, and they are asked us to find the uh, infiltration depth in centimeter after 30 minutes. So now here we need to find T equal to 30 minutes, that is equal to 0.5 hours, right? That is F for 0.5, nothing but S is given by 5 centimeter per hour, right, into 0.5 raised to half. Hydraulic conductivity K is given in the question, that is equal to hydraulic conductivity is equal to 0.4 centimeter per hour. So it is a given in the question. K is equal to 0.4 centimeter per hour, right? So if you substitute that, we will be getting 0.4 into 0.5. So this will be somewhat nearly 5.5355 plus 0.2. And if you take the sum, f at 0.5 will be 3.7355 centimeter. So this is the infiltration depth that you will be getting after 30 minutes if the column was kept vertical. So after 15 minutes when the column was kept horizontal, the infiltration depth was 2.5 centimeter. Same experimental setup, if you keep it in the vertical direction, the depth we will be getting after half an hour will be equal to 0.7355. Okay. So we have to report the answer in two decimal places. It has to be reported in two decimal places. So if you want to report in the two decimal places, in 0.5 will be 3.74 we can write, right, limit. So this is how so only thing you have to remember, the Phillips equation, the advantage is that it can be applied for a vertical column and also we can be applied for a horizontal column. When we apply for a horizontal column, the gravity term, so we already saw what are the two terms involved. The gravity term will be vanishing. It will be already having the suction term. And the suction term, using that we can find the parameter, this optivity. We can use that same parameter for the vertical cliffs. If we know the hydraulic conductivity also, we can find the depth of infiltration happening or cumulative infiltration happening at any time. Okay, so we will move on to the final question. This question is something what related to the Greenham method. So Greenham method is also an analytical method, or we can say it is also a theoretical method to find the infiltration rate or cumulative infiltration depth. Okay, so the Greenham method basically you saw already saw Phillips equation that they were making use of the infinite series approximation, right? In Greenham method to resolve Richard's equation, we are doing that. We are solving it analytically. Okay, so basically we can through this question, solving this question, we will be introducing you through the Greenham method. Okay, so compute the infiltration rate in centimeter per hour. Okay, rate you have to find small ft. Exactly exactly 1 hour after exactly 1 hour of infiltration into a silt loam soil. This type of soil is given, that is silt loam soil. The soil initial had a effective saturation. So effective saturation is 30%. The SC is already we got. No, right, we in the previous question, we already calculated SC, right? SC is nothing but the ratio of how much excess moisture is currently present in excess to the residual moisture content and how much maximum excess moisture can be added to make the moisture maximum, that is to reach porosity. So that ratio is called effective uh, saturation. So that is given in the question, that is given as SC is zero point 0.3. Assume water is ponded at negligible surface depth. So the ponded depth can be assumed neglected for a silt soil, loam soil. So the soil type is silt and loam. The effective porosity, so theta E value is given as 0.486, and the wetting front soil suction head. So the suction head is given as 16.7 centimeter, and the saturated hydraulic conductivity K is given as 0.65 centimeter per hour. Use Greenland infiltration model and iterative substitution to solve the cumulative infiltration before calculating the rate. So basically, we need to find the infiltration rate and the cumulative infiltration. Okay, and we have to report the rate in centimeter per hour. Right. So if I if you have seen the lectures, the equation of using renamed method using renamed method, the capital F of t is given by kt plus psi delta theta into ln 1 plus f of t by psi delta theta. So this is the equation that we had derived or we have seen in the lecture classes uh, for finding the infiltration rate. So the problem with this equation was that the infiltration cumulative depth was there in both the sides, right? So it is a nonlinear implicit equation. The implicit nonlinear equation. We cannot directly find the value of f of t by solving, right? So such will be solving with the help of numerical methods. Basically, we'll be using numerical methods. We will solve for f of t, right? So we can see the terms K is given, hydraulic conductivity is given, and K is given as uh, K is given the question as 0.65 centimeter per hour, and we are asked to find the infiltration after 1 hour, right? So T is 1 hour. So we have the term KT coming. So K into T will be 0.65 centimeter, right? So we can directly substitute that here. And then psi is already given the question. Psi is nothing but the suction head is 16.7 centimeter, right? And then there is another term called delta theta. So what is delta theta? So delta theta is the change in moisture content, change in moisture content. Delta theta has a relation 1 minus AC effective moisture into theta E, effective saturation into theta E. This is the equation for delta theta. So 1 minus effective moisture Effective saturation is given by point is given in the question as zero point 0.3, right? Theta E is equal to 0.3 and not theta E, SC is given as 0.3, that is effective saturation, and effective porosity is given by 0.486. 0.486. So these will be given like these are fixed for soil. These are values for loamy soil, right? So this is a silt loam soil. So different soil parameter, soil texture type, we have a different values of these values are fixed. So these are given the question. So we can directly substitute and find the change in moisture 486. So this will be coming around 0.3402, right? So once that is there, so we can see this value, that is psi delta theta is repeating. So psi delta theta we can find it out. So psi delta theta is nothing but 16.7 into 3, 0.3402. That will be approximately 5.68 centimeter. I can substitute that also. So if I substitute that in this equation of f of t, kt is nothing but 0.65 plus psi delta theta, I got a 5.68 into ln inside bracket 1 by, so if I write f of t as f, for simplicity I'm going to solve for x, 1 plus f by 5.68. So now we got an equation. This is a nonlinear implicit equation. Now we can apply the numerical methods. So one of the numerical method which I will be discussing in this lecture, this is the trial and error method. So numerical method, one of the simplest method, straightforward method is trial and error. What we do here is we will substitute make some assumptions and substitute that, and we'll see whether the LHS and RHS are matching. For example, this f is given by this particular equation, right? So here we'll assume some value for this particular f. We assume some value and we see whether the LHS and RHS are matching. For this, we will assume some value and see whether LHS and RHS are matching. So that is what we do in case of a trial and error method. So keep in mind, you can always you can see here it has a two terms are there. F is sum of 0.65 into another term. So let's assume F is equal to, so this is our trial one, F is equal to 0.65. So this is the first trial. We are assuming our F is equal to 0.65, right? So we can substitute in this particular equation, then we can get F is equal to 0.65, 5.68 ln 1 plus we'll be substituting here. Okay, so here we'll be substituting it as 0.65 divided by 5.68. So when you solve this, you will be getting this around 1.27 centimeter. So the assumption that we made was f is equal to 0.65, and it is very much different from 0.65, right? So this will be wrong. So next in trial 2, we will assume f as, so we'll be assuming f as 1.27, whatever we got it here, right? Then we can find x, f is equal to 0.65, that is kt, 5.68, that is nothing but delta 5, 1 plus, and we will be substituting that f here, 2.7 divided by 5.68. So this if you solve, it will be coming around, in solve it in calculator, it will be coming around 1.79, and this is also not equal to 1.27, right? So it is our assumption and whatever we are getting from the trial is not matching, but still the error is less compared to what we got, the error we got here. So error is nothing but The what we assume, what we got, 27 mod of minus 0.65. This is our error. Now the error is 1.79 minus 1.27. So the error is less, right? So it is reducing. So next we can assume this value. So this was our trial 2. Now it is going to a trial 3 or iteration 3. Okay, so there we assume f is equal to 1.79. Then f will be equal to 0.65 plus 5.68 ln 1 plus, here we will be substituting 1.79 divided by 5.68. That if you solve, it will be coming around 2.2, still not equal to 1.79. So error has further reduced. So if you continue this, so for as the time it's not there, I'm not solving for the other. It after some time the value will be to converging, and we'll be getting finally f is equal to 3.17 centimeter. So this is the cumulative infiltration depth uh, after 1 hour of infiltration happening. Okay, using the green app method. So finally, if you want to find the infiltration rate corresponding to this infiltration depth, there is a formula. If we had seen the lectures, I must introduce you to a formula. That is, infiltration rate is given by K into 1 plus psi delta theta divided by F, right? K is nothing but 0.65. That is a hydraulic conductivity centimeter per hour. 1 plus psi delta theta we already found out 0.68, and F we got it as 1.17. So whatever we are getting here, that is equal to 1.814 centimeter per hour. That is our infiltration rate. So therefore, F after 1 hour is equal to, we round it off two decimal places, 1.61, 1.81 centimeter per hour. Okay, so this is the green damp method. So the equation that we will be deriving, the solution for the Richards equation will be somewhat looking like this. The only problem is the Ft is a implicit nonlinear equation. Ft is coming in both LHS and RHS, and we cannot separate it out. So we'll be solving this using the numerical method, one of the simplest method, which I introduced is a trial and error method, where we'll be assuming. So the first assumption that you can take it as KT, and then we further keep on updating, and after further trials this starts converging, and the final answer will be getting it around 3.17. You can follow the other trials, it will be converging in the fifth or sixth trial to be nearly equal to 3.17. And if you have the cumulative depth, and if you know the hydraulic conductivity and also the suction head and the change in moisture content, we can find the infiltration rate using this particular relation. Okay, so you'll be getting it around 1.81 centimeter per hour. So I'm stopping it here. So we have all covered the entire portions that we started with the infiltration process, what is infiltration and how we can measure infiltration, how our infiltration is represented. Then we saw the estimation, different methods to estimate infiltration, empirical equations we saw, and also the theoretical, that is the Phillips equation and the what are the advantages of Phillips equation, and then we finally saw the green amp method. Okay, so if you have any further doubts during this section, you can contact me through my mail. My mail ID is akhiljanadevan@gmail.com, AKHILJNANADEVAN@gmail.com. My name is Akhil. Okay, then I'll be uploading this content, this PDF in the drive folder. So if you have any doubt, you can contact me through the mail. So thanks for joining. I'm stopping this section.